Welcome to the Chemistry, Biology and Math Revision Hub. Today we're doing the Pearson Edexcel International GCSE Chemistry Paper 2C for November 2024. Let's begin with the first question. In question 1, the table shows the composition of 5 species that are either atoms or ions. So how can we tell if they're ions? Of course, if the number of electrons and the number of protons are not the same, then those are going to be ions. For example, A is not, B is not, C is not, D is, because there are 9 protons and 10 electrons, so this is negatively charged. E is not as well because the number of protons and electrons are exactly the same. So they say use the table to answer these questions. You may use each letter once, more than once, or not at all. The first part says give the letter of the species that is a negative ion. Like I've already said, D is a negative ion because it has more electrons than protons. Then give the letter of the species that has a full outer shell of electrons. When we look at the configuration, these are 3 electrons, so 2, 1, and then here 2, 1, here 2, 8, and then 2, 8, 3, so this has a full configuration. Again, the answer is D. And then give the letter of the species that has an atomic number equal to its mass number. Remember, mass number should be number of protons plus number of neutrons. So in this case, we can see this one here. Number of protons plus neutrons equals to 1, and the number of electrons, or in this case number of protons and electrons, are equal, which are also equal to the atomic number, so the answer should be A. In part B, explain why species B and C are atoms of the same element with identical chemical properties. To have identical chemical properties, it means they have the same electronic configuration or same number of electrons. So I say they have the same number of protons, which are 3, so they are the same element. They have the same electronic configuration, so their chemical properties are identical. Their different neutron numbers make them isotopes as well. Then in part C, they say a proton has a mass given here. A neutron has this mass as well. They want you to calculate the mass in grams of the nucleus of the atom with C in C. So here this has 3 protons, 4 neutrons. We're going to use that. So the mass is going to be 3 times the mass of protons plus 4 times the mass of neutrons. You can also round off to 3 significant figures as you wish. In question 2, this question is about metals and metal compounds. All metals are malleable and good conductors of electricity. The diagram shows the structure of a metal. Now within this metal, we have the metal ions, which are cations and the delocalized electrons, because there is metallic bonding here. They say explain why metals are malleable. Metals are malleable because when a force is applied, the layers of ions slide over each other, but the electrons remain holding them together, so the structure doesn't break. So I said layers of metal ions can slide over each other without breaking the metallic bonds holding the structure together. And then explain why metals are good conductors of electricity. To conduct electricity, we either need free ions or free electrons. So in this case, we have free electrons. The ions are not moving, but the electrons can move, so they contain delocalized electrons. These electrons are free to move and carry electrical charge through the metal. Then part B, 2 methods of obtaining a metal from a compound are electrolysis and extraction using carbon. Explain without giving practical detail which method is more suitable for extracting iron from iron 3 oxide. In the extraction of iron from its ore, they usually heat their iron ore with carbon. Because carbon is more reactive than iron, it's going to replace it from its compound to form carbon monoxide and carbon dioxide. In the end, of course, you form carbon dioxide, and then iron is going to be left as a metal. So I said carbon extraction is more suitable because carbon is more reactive than iron, so it can displace iron from its oxide. Electrolysis is unnecessary for metals below carbon in the reactivity series. Then part C, a student has a solution of iron 2 sulfate and a solution of iron 3 sulfate. Describe a chemical test the student could use to identify the solution of the iron 2 sulfate. Here you're going to react each of the solutions with sodium hydroxide and then observe the colors of the precipitates formed. So with iron 2 sulfate, it's going to be a green precipitate of iron 2 hydroxide, and with iron 3 sulfate, it's going to be a brown precipitate. But of course, you have to be very careful because this iron 2 sulfate could be oxidized till a little bit turn brown, but it's going to be green. Then question 3, a teacher uses this apparatus to separate a mixture of ethanol and water. This is fractional distillation. We can see inside here we have a fractionating column. So they say give the name of this method of separation. This is not chromatography, it's not crystallization or filtration, it's fractional distillation. So the answer should be D. And then name the piece of apparatus labeled X, Y, and Z. If you go back here, this is a thermometer, this is a labeling condenser, or you can just say condenser, and this is a beaker which is going to be used to collect the sample. So thermometer, condenser, or labeling condenser, and then a beaker or receiving vessel. Then in part C, give a physical test that the teacher could do to find out if the ethanol produced is pure. In this case, ethanol is a liquid, so you do a boiling point determination, and the boiling temperature of ethanol is 78. So if the liquid boils at 78 degrees, then you can confirm that this is pure ethanol. If it's not pure, then it's going to boil over a range of temperatures. In question 4, a teacher adds a small piece of lithium to water and collects the gas produced. Give 2 observations when lithium is added to water. There is going to be fizzing as hydrogen gas is produced due to the reaction between water and lithium. Also, the lithium is going to float because its density is less than the density of water, so it's going to float and move on the surface of the water. It will get smaller, and finally it will disappear after it has completely reacted with the water. Then next, the teacher adds a few drops of universal indicator to the solution at the end of the reaction. Explain the final color of the universal indicator. When this reaction takes place, lithium hydroxide and hydrogen are produced, and the lithium hydroxide is going to be an alkali, so we expect the universal indicator color to turn purple. So I said purple. Lithium forms lithium hydroxide, which is a strong alkali, increasing the pH and turning the indicator purple. In part B, this is the equation for the reaction between lithium and water. We can see it there. The teacher collects 550 centimeters cubed of hydrogen at room temperature and pressure. Calculate the mass in grams of lithium that the teacher added to the water. They've given us that 1 mole of a gas at room temperature and pressure has this volume, the AR of lithium, as well as carbon, hydrogen, and oxygen ARs. Since we're given the volume of hydrogen, I'm going to use this to find the number of moles of hydrogen. So number of moles of hydrogen will be the volume given divided by this, giving me 0.0229 mole. And then I'm going to use the mole ratio, which is 1 to 2. So moles of lithium should be twice these moles. So multiplying through by 2, I get that. And finally, the mass, which is going to be number of moles, times the relative atomic mass. I got that times 7, giving me 0.321 grams after rounding off. And you can round off to be 0.32 grams to 2 decimal places. Then the teacher then adds a small piece of potassium to water. Give 1 observation seen with potassium that is not seen with lithium. The flame here is going to be lilac. So this explains why potassium is more reactive than lithium. Refer to the atomic structure in your answer. If you look at the atomic structure of potassium, it has more shells in comparison to lithium. So the outer electrons in potassium are farther away from the attraction of the nucleus and therefore easily lost. So I said potassium has more electron shells, so its outer electron is farther from the nucleus. There is more shielding from the inner electrons. The outer shell is less strongly attracted to the nucleus, so its outer electron is lost more easily, increasing reactivity. In question 5, a student does some titration to find the volume of dilute nitric acid needed to exactly neutralize 25 centimeters cubed of sodium hydroxide solution. This is the student's method. In step 1, add 25 centimeters cubed of sodium hydroxide solution to a conical flask. In step 2, add 3 drops of methyl orange indicator. Step 3, fill a burette with the acid. Step 4, add acid from the burette until the indicator changes color. And step 5, record the volume of the acid added. Then they say give the name of the apparatus that the student should use to measure the volume of sodium hydroxide used. This should be a volumetric pipette. So they say give the color change in step 4. This is going to be from yellow to red. They're using methyl orange indicator. And then give a reason why the student does not use universal indicator in this titration. Using universal indicator, there is no sharp color change, so the endpoint will not be detected properly. So I said it gives a range of colors and not a sharp endpoint. making it hard to determine when neutralization is complete. Then in part B, the student completes a rough titration, and for accurate titrations, the diagram shows the burette readings from the rough titrations. So here the reading is about 2.15, and the reading here is about 23.8. So they say the table shows the students' results. We see them here, minus those in blue. I just filled them. They say complete the table by adding the results from the rough titration. Record the volumes to the nearest 0.05 centimeters cubed, meaning 2 decimal points. So from previously, I read from the burette 23.80 in 2.15. Subtracting, I got 21.65 as the rough titer. And then they say concordant results are results within 0.2 centimeters cubed of each other. Use the concordant results from the table to calculate the mean volume of acid added. So for my observation, I saw it was titer 1 and titer 3 which were concordant. If you get a difference between these and a difference between that as well as those, the values are going to be more than that, so they do not qualify as concordant results except titration 1 and titration 3. So we can use those to get the mean titer. So we will add that plus that and divide by 2 to give us 21.40 centimeters cubed as the mean volume of the acid. Then in part C, this is the equation for the reaction between dilute nitric acid and sodium hydroxide solution. We see the equation here. They say after the titration, the student knows the volume of the acid needed to neutralize 25 centimeters cubed of sodium hydroxide solution. Sodium nitrate decomposes at high temperature. Describe how the student could obtain pure dry crystals of sodium nitrate from dilute nitric acid and sodium hydroxide solution. So this means they're going to add the two solutions based on how exactly they react, but without the indicator. Allow them to react, then evaporate off some amount of water so that the crystallization point is reached. Of course, you're going to heat gently since it decomposes. And after you filter the crystals and then dry them with filter paper, or you could use a warm oven, so I said, repeat the titration using exact volumes of sodium hydroxide, and the acid, no indicator this time, gently heat to evaporate some water from the solution using a water bath until crystallization point. Then leave the solution to cool and crystallize. Filter the crystals and dry them using filter paper or in a warm oven. In question 6, this question is about crude oil. Describe how crude oil is separated into fractions by fractional distillation. Here, simple, we're just going to heat the crude oil, and then the vapors are going to rise through the column. The vapors will enter the fractionating column with a temperature gradient, meaning the hot ones are going to be at the bottom and the cool ones are going to be at the top. The different hydrocarbons are going to be condensed at different levels depending on their boiling point, and each fraction is going to be cooled as it condenses at a specific level. Then part B, some of the long chain alkanes obtained from fractional distillation are cracked, producing shorter chain alkanes and ethene. Give the conditions necessary for cracking to occur. For cracking, we need high temperatures between 600 to 700 degrees Celsius, and we need a catalyst which could be silica or alumina. Then explain why shorter chain alkanes are more useful than longer chain alkanes. The shorter chain alkanes are more flammable, or you could say they are more volatile, so they can be used successfully as fuels. They are also easier to transport, but the main answers are they are volatile, so they can be useful as fuels. Then ethene reacts with bromine. The equation shows the displayed formulae of the reactants and products. We can see them here. The table shows some bond energies. We see them as well. Then they show that the molar enthalpy change, delta H, of this reaction is about negative 100 kilojoules per mole. So in this reaction, we can see the carbon-carbon double bond is 1, the carbon hydrogens are 4. Here we have the bromine-bromine, which is 1 from the reactant side. The product side, we have carbon-carbon single, which is 1, and then we have 4 carbon hydrogen and 2 carbon bromine. So they are all listed here. But since these are 4 and here we have 4, so I canceled them out to make life easier. And now I'm just going to use that for the reactant, and then that for the product. So the total bonds broken are going to be 1 times into the enthalpy of the carbon-carbon double bond plus 1 times into the enthalpy of the BR-BR, giving me 805 kilojoules per mole. And the bonds formed are going to be 1 times the carbon-carbon single, which is 348, plus 2 times the carbon Br, which is 276, giving me 900 kilojoules per mole. So the enthalpy change should be the summation of bonds broken minus summation of the bonds formed, giving me negative 95 kilojoules per mole, and this is closer to negative 100 kilojoules per mole. Then explain why the reaction between ethene and bromine is exothermic. Refer to the bond energies in your answer. So in the answer we can see this is a negative value, meaning it's exothermic. That means the total bonds that are broken, meaning the endothermic requiring breaking of the bonds, the energy required was less than the energy released as the bonds formed. So I say the energy released from forming new bonds is greater than the energy needed to break the old bonds. This results in a net release of the energy to the surrounding. In question 7, this question is about alcohols and carboxylic acids. These are the structure formulae of alcohol A and carboxylic acid B. They send them alcohol A. This is propan 1O. It's an alcohol with 3 carbons and the OH is at the end, so propan 1O. And then they say draw the displayed formula of the alcohol A. In displayed formula, we display all the bonds. So this is CH3, CH2, CH2, and then OH. All the bonds are displayed out. And they say carboxylic acid B has a chain of carbon atoms with no branches. Calculate the value of N. They've given us the MR, 242. So writing this and equating it to 242, where N is going to be multiplying that. So this carbon is 12, 3 hydrogen 3, and then whatever is inside here is 14, 12 plus 2, multiply that by N, plus the carbon 12, and then 2 oxygens, 32 in 1 hydrogen will give us 242. So when I add it up, I got 14N plus 60, giving me 242, and 14N will be 182, dividing through, I got 13, so N equals to 13. Then alcohol A and carboxylic acid B react together to form an ester. Give the other product of the reaction. This is an esterification reaction, so when an alcohol and a carboxylic acid react, we get an ester and water, so water should be the answer. And then these are structural formulae of dicarboxylic acid C and diol D. We can see them like that. This is the equation for the reaction between dicarboxylic acid C and sodium hydroxide solution. So we see we are forming a salt and water. They say 25 centimeters cubed of 0.15 mole per decimeter cubed sodium hydroxide solution is completely neutralized by 17.5 centimeters cubed of a solution of dicarboxylic acid C. Calculate the concentration in mole per decimeter cubed of the solution of dicarboxylic acid C and give your answer to 3 significant figures. So since I have the components for sodium hydroxide, I'm going to begin from here. Moles of sodium hydroxide should be the concentration times the volume, but the volume should be converted to decimeters cubed. That's why I divide by 1000 and I got that. And then the moles of the acid, we use the mole ratio, which is 2 to 1. So moles of this should be a half the moles of that. So 1/2 times these moles, giving us that. And finally, the concentration of that should be number of moles of our volume, which is these moles, divide by the 17.5. But again, I multiply by 10 power negative 3 to convert it to decimeters cubed. And finally, I got 0.107 mole per decimeter cubed. So that was my answer here. And next they say that carboxylic acid C and diol D react to form a polyester. Draw the displayed formula of the repeat unit of this polyester. We can see the dicarboxylic acid and the diol. When they join together, the alcohol loses the hydrogen, but the carboxylic acid loses the OH. So this is going to be left in between them. But also to form the repeat unit, the carboxylic acid side should lose the OH, and the alcohol side should lose the hydrogen, creating what we see here. So this brings us to the end of question 7, as well as to the end of the whole paper. Thank you for being with us. Do not forget to subscribe. See you in the next video. Bye-bye.